Okay, so for this webinar we're going to discuss the post hoc analysis of an ANOVA using the Tukey test, and then we'll also look at a non-parametric ANOVA using the Crustal-Wallace method, and then we're going to look at the follow-up to the Crustal-Wallace for trying to determine differences between groups or treatments using the Mann-Whitney U-test. A little statistical background. ANOVAs, there's parametric and non-parametric ANOVAs. Most of your complete randomized block ANOVAs are typically conducted when you're looking at 3 or more means in an experiment. Your results of an ANOVA are going to determine if there are significant differences between groups. After you prove that significance exists from that ANOVA, you're going to normally run either mean separation or orthogonal contrast after the fact. If the ANOVA rejects the null hypothesis, you can use the mean separation for determining differences amongst groups. The optimal post-ANOVA analysis for unstructured data would most likely be a Tukey test, which is what we're going to look at with this webinar. Now, mean separation differs from orthogonal contrast in that mean separation looks at unstructured data. Orthogonal contrast are looking at structured data, which, in other words, as an example, if we have unstructured treatments, we might have research that has 3 treatments, such as a control where no treatment is applied, it's left as is, mechanical treatment such as mowing, and a chemical treatment. With these unstructured treatments, there is no basis for combining any of the treatments together to compare to others. Now, in research that I'm looking at, the experimental design is a complete random block, but there are 6 experimental treatments inside of a block. Now, we have a control, but then we have 3 treatments that are only utilizing one type of herbicide, and then you have 2 treatments, the control or the banded plus SFM and radial plus SFM, which are actually utilizing 2 herbicide treatments. In this situation, you have structured data to where we could say, do the applications with one herbicide differ from the applications that have 2 herbicides? And typically with contrast, you have to be able to ask hypothetical questions, the same amount of hypothetical questions as you have of degrees of freedom. So in this case, we would need to be able to ask 5 potential questions. So another question might be, does control differ from all other herbicide treatments? But you have to figure out what those 5 are. But for this instance now, we're going to talk about mean separation. So when we're trying to decide a mean separation technique to use, it is preferred to have an experiment-wise error control over a comparison-wise error control. The experimental-wise error control is going to set the type 1 error rate for all the comparisons that are made. Normally, a researcher is going to establish a 95% level or a p-value of 0.05. With the Tukey honest significant difference test is normally the most preferred by journal reviewers. It also has a moderate power rating, but what it'll do for you is determine where the differences between your individual groups lie, or in between your treatments. It allows you to pinpoint which exact group are actually significantly different from one another. But it only does it one treatment versus one treatment at a time, where contrasts allow you to look at combinations of treatments. Your results, you want to find an F-value that is normally greater than 5 and a p-value that is below your significance level, or right at. So let's look at a little bit of code. This is your basic code to be able to download or upload a file into the R program. In this case, I named mine total seedlings and then named the data file seedlings. So this is kind of what we're looking at as far as analysis. The main thing that we're going to focus on with this data are the treatments, which is your second column, and the diameter change, which is on the top, the far right column. And what that diameter change is basically the trees were measured for ground line diameter in year 0, the fall after the harvest, the end of the growing season, and then 2 years after that they were remeasured, and that change in growth is the difference from the first measurement to the second measurement. But that's what we're going to analyze in this webinar. And up top you see in blue, that's the code that is entered into R. This is basically taken out of R and copied into the PowerPoint so that I don't have to jump back and forth between the PowerPoint and R. But that's the code that you would use to pull that up. Now, we're going to run an ANOVA to see if there's any differences between the treatments, the species, or the interaction between the treatment and species. And there's the code up top, and then to get it to print out, we did the summary of what I named it as article. In this output, the ANOVA table, you see that there is a significance difference between the treatments. So now that we know that there is a significant difference between treatments, it allows us to do a mean comparison. So what I did was I reran an ANOVA just looking at the diameter change by treatment, and then I printed out the ANOVA table. Same values as with the larger ANOVA, but it allows us to say yes, there's a difference, so we can proceed. So now I ran the Tukey. You see the code at the very top upper left, Tukey HSD and article in parentheses. So this is the output that we got from R, and I've highlighted some of the larger values. So let's look at the radial SFM compared to the banded, the first yellow, the higher yellow in that column. And what that is saying is that there was a difference between the radial and the banded plus SFM treatment of 0.20, let's just call it 0.208, which was one of the larger ones, and the very largest was the radial compared to the SFM control of 0.263. Now basically you see the ones in blue now that are comparing the banded, which was a single herbicide, to an SFM banded, which was the 2 herbicides, and you see that it had a little greater growth just with the banded. And then on the bottom, the radials plus the SFMs were larger than just SFM and the radial alone. So what we can surmise from that, now you see there's some negative values in there too, but basically what this is saying is, in general, with a higher intensity of herbicide application, i.e. when we have 2 applied herbicides, normally we're going to yield greater growth, especially with the radial release applications in conjunction with the SFM 75. Now we want to plot that also, so the code is at the very top. You see how we have the plotted codes, and only one of them was not different, which that was, we're looking through this column here and we're looking for, it was the radial and the control SFM 75, which is between the yellow and the blue highlighted areas on the bottom. So there was no difference between those, but every other treatment was significantly different. If that line falls on the 0 line, it's saying that there was no significance between the compared treatments. Now, if we want to run a non-parametric ANOVA, we might look at using the Crustal-Wallace method. This is an equivalent, a non-parametric equivalent, to the one-way analysis of variance. We're going to use this if all the samples are taken from the same location. And it can also be used if the samples have the same shape and equal variances. There are 3 primary requirements to being able to use the Crustal-Wallace. 1, the samples are random and are independent. 2, there are 5 or more measurements per sample. And 3, the probability distributions are continuous. So, if we have data, let's say we have a smaller data sample size, we can utilize this method, but one of the drawbacks is normally it's going to be more conservative and it's going to have less power compared to a parametric ANOVA such as your complete block. There's also a higher likelihood of making a type 2 error when you use a non-parametric method. The test, the Crustal-Wallace test, is a version of the independent measures or one-way ANOVA that can be performed on ordinal data. We normally use this to find out if there's a difference between multiple groups or treatments. So very similar to the parametric methods, but less power, more conservative. The purpose of the test is to test for differences in central tendency. So unlike with parametric, we're not looking at means or median when we use Crustal-Wallace. This utilizes a chi-square value and degrees of freedom to determine significance. So for our example, we had 6 treatments, 6 different herbicide treatments, which includes the control, which leaves us with 5 degrees of freedom. If we look at a chi-square distribution table, we determine we need a chi-square value greater than a little over 11 to be significant at the 0.05 level. So we run the Crustal-Wallace test, and the code is in the upper left there. Crustal.test by diameter as by treatment from the data set. Now this ranks the data and then it's going to do the number crunch. We came up with a chi-squared value of 2125 and it's highly significant. So that tells us that yes, this test is saying there is a difference between treatments. So now we have to come up with a way to do comparison between the groups. And the Mann-Whitney test is going to be the best way, or actually the only solution, to compare individual groups against one another. This is normally the way that you would do non-parametric testing. It must use an adjusted alpha, such as the home correction method. This is normally the preferred method for this technique of non-parametric post hoc testing, and it's also the default setting in R. So here we ran the code pairwise. I do not know why it's Wilcox and not Mann-Whitney, but that's how it's set up in R. And we did the diameter change and the treatments, compared those. So then we get this pairwise comparison, and it shows each one of the individual treatments. So as we look through the table, we see that all of the treatments are different from one another, with the exception of the radial compared to the control with the SFM treatment. It was not statistically significantly different. So that's how you would run the non-parametric method of ANOVA, and then also the post hoc testing. I thank you, and have a good day.